There's a planet at the edge of the solar system that no telescope has ever seen. We know it is there because of what it is doing to everything around it. This is not speculation. It is not the kind of claim that belongs on the fringe of planetary science. It is the conclusion of a research program begun in 2016 by Konstantin Batygin and Mike Brown at the California Institute of Technology, two of the most rigorously credentialed planetary scientists in the field. Built on orbital mechanics, statistical analysis, and a pattern in the data that has grown more difficult to explain away with each passing year. A planet exists in the outer solar system, beyond Neptune, on an orbit so distant and so elliptical that its closest approach to the Sun brings it no nearer than approximately 250 times the Earth-Sun distance, and its furthest point recedes to perhaps 800 or 1,000 times that distance. At that range, it would take between 10,000 and 20,000 years to complete one orbit. It has never been photographed. Its position in its orbit right now is unknown, within a region of sky covering roughly 1/5 of the entire celestial sphere. It may be the most consequential undetected object in the history of planetary science. Konstantin Batygin is a planetary astrophysicist at the California Institute of Technology, whose research focuses on the dynamics of planetary systems, how planets form, how they interact gravitationally, and how the architecture of a solar system evolves over time. He is also, by his own account, someone who spent the better part of a year trying to find an alternative explanation for the anomalous clustering of Kuiper belt objects before concluding that no alternative was adequate. Mike Brown, his collaborator, is the astronomer responsible for discovering Eris, the Kuiper belt object that triggered Pluto's reclassification as a dwarf planet. He describes himself on social media as the man who killed Pluto. Together, they represent a combination of theoretical rigor and observational experience that makes their case for Planet 9 something the planetary science community cannot dismiss, even when it disagrees. For most of the 20th century, the solar system was understood as a closed and settled system. 9 planets, or 8 after 2006, arranged in well-understood orbits, governed by well-understood physics, their dynamics mapped to the precision of centuries. The Kuiper belt, once discovered in 1992, added a new structural layer, a disk of icy bodies beyond Neptune's orbit, collectively representing the remnant building blocks of the outer solar system. By the 2000s, thousands of Kuiper belt objects had been cataloged. Their orbits were being systematically characterized. The picture was one of gradual completion, not of dramatic surprises, but of filling in the details of a structure whose broad outline was already known. Planetary scientists did not expect another planet. The outer solar system was mapped. What remained was inventory. That expectation was shattered in January of 2016. Batygin and Brown published a paper in the Astronomical Journal, presenting evidence that 6 known Kuiper belt objects distant, high perihelion objects whose orbits reach furthest from the Sun, were clustered in physical space in a way that had less than a 1 in 10,000 probability of occurring by chance. The objects were not randomly distributed around the Sun, as they should be if their orbits were shaped only by the known planets. They were bunched together, their orbital planes and orientations aligned in a configuration that could only be maintained against the gravitational disruption of the rest of the solar system if something massive was actively shepherding them. Something with a gravitational influence strong enough to herd distant Kuiper belt objects into a coherent cluster over billions of years. Something, Batygin and Brown concluded, with a mass somewhere between 5 and 10 times that of Earth, on a distant, inclined, retrograde orbit that keeps it on the opposite side of the Sun from the cluster it is producing. The evidence stack has grown significantly since 2016. The clustering signal, initially based on 6 objects, has been examined, challenged, extended, and partially qualified as the Kuiper belt catalog has expanded. By 2023, the number of extreme trans-Neptunian objects with orbits consistent with the clustering signal had grown to more than 30. Each new detection is a new data point that either fits the pattern or does not. The majority fit. Critics, including Stephanie Clement at the University of Michigan and Pedro Bernardinelli at the University of Washington, have argued that the clustering could be an observational bias, that the objects were found because telescopes were pointed in a region that made them discoverable, not because they are genuinely clustered. Searches for Kuiper belt objects are not uniformly distributed across the sky. Telescopes point where conditions are best. where survey programs have allocated time, where previous discoveries suggested further objects might be found. A bias in where we looked could produce apparent clustering in what we found. Badigan and Brown have responded to this criticism in extensive detail, modeling the survey biases of every telescope that discovered the relevant objects and running simulations to determine how much of the clustering survives when bias is accounted for. Their conclusion is that observational bias explains some of the clustering, but not all of it. The debate continues. It is an honest scientific debate between researchers using the same data and reaching different conclusions about what that data proves. That is what the scientific process looks like from the inside. What has strengthened the Planet 9 hypothesis beyond the initial clustering signal is a second, entirely independent set of phenomena that the hypothesis also predicts. In 2016, Badigan and Brown noted that a planet on the predicted orbit would gravitationally excite a population of highly inclined trans-Neptunian objects through a mechanism called secular resonance. Objects caught in this resonance would have their orbital inclinations, the angle at which their orbits tilt relative to the solar system's main plane, steadily pumped upward over hundreds of millions of years, eventually reaching the extreme tilts observed in a handful of known objects. Some of these objects orbit nearly perpendicular to the plane of the solar system. A few orbit in retrograde backwards, relative to every other major body in the solar system, in apparent violation of the angular momentum that the solar system inherited from its formation. These objects were discovered before the Planet 9 hypothesis was formulated. The hypothesis predicted them after the fact as a natural consequence of the proposed planet's gravitational influence, without any additional tuning of the model. Predictions that account for pre-existing unexplained observations without being specifically designed to explain them carry particular weight in evaluating a scientific hypothesis. This is one of the stronger arguments for taking Planet 9 seriously. A third line of evidence emerged in 2019 when Elizabeth Bailey, Batigan, and Brown demonstrated that Planet 9's predicted gravitational influence, acting over the age of the solar system, would tilt the solar system's orbital plane by approximately 6 degrees relative to the Sun's own equatorial plane. This tilt, the fact that the planet's orbit in a plane inclined 6 degrees to the Sun's spin axis, has been precisely measured and known for decades, and has never been satisfactorily explained. The Sun's spin axis and the planetary orbital plane should, by the logic of solar system formation from a rotating disk of gas and dust, be almost perfectly aligned. They are not. Every proposed conventional explanation for the misalignment requires implausible fine-tuning or invokes processes too weak to produce the observed effect. Planet 9's secular gravitational influence on the planetary system naturally produces exactly the observed tilt over 4.5 billion years. For a planet with the predicted mass and orbital parameters, the match is not constructed to fit the observation. It falls out of the physics of the proposed orbit applied to the known solar system. That three independent anomalies, the clustering of extreme trans-Neptunian objects, the population of high-inclination retrograde objects, and the 6-degree tilt of the solar system are all explained by a single object on a single orbit, is the core of the statistical argument for Planet 9's existence. The countercase is substantial and must be taken seriously. The clustering bias argument, made most forcefully by Clement and by Pedro Bernardinelli at the University of Washington, remains unresolved. The Legacy Survey of Space and Time at the Vera Rubin Observatory, a wide-field optical survey beginning in 2025 that will catalog tens of thousands of new Kuiper Belt objects within its first few years of operation, is expected to either dramatically strengthen or definitively weaken the clustering signal. If the clustering disappears as survey bias is accounted for across a much larger sample, the primary evidence for Planet 9 weakens substantially. The orbital tilt and high-inclination object explanations are real constraints that require explanation with or without Planet 9. But alternative mechanisms, primordial solar capture of a rogue planet, a passing stellar encounter in the early solar system, or statistical fluctuations in the known giant planet dynamics have been proposed and cannot yet be ruled out. What Batigan and Brown have done is identify the most parsimonious single explanation for multiple independent anomalies. What they have not done is eliminate all alternatives. Science rarely works faster than that. If Planet 9 exists, finding it is the primary challenge, and it is a formidable one. The object, if real, is expected to be between 5 and 10 Earth masses, roughly comparable to Neptune in mass, though possibly denser and smaller in radius if it has a higher proportion of rock relative to ice. At its estimated current distance, somewhere between 300 and 700 astronomical units from the Sun, depending on where in its approximately 10 to 20,000 year orbit it currently sits, it would be extraordinarily faint. The apparent brightness of a solar system object falls off with the fourth power of its distance. Twice as far means 16 times dimmer. A Neptune-sized object at 500 astronomical units, reflecting a fraction of the sunlight that makes Pluto detectable at 40 astronomical units, would be at the very edge of what current wide-field survey telescopes can detect. Current surveys have been explicitly searching for it since 2016, without a confirmed detection. Either it does not exist, or it is currently in a part of its orbit that makes it too faint to find with instruments deployed so far. Both possibilities are consistent with the data. The Vera Rubin Observatory's Legacy Survey of Space and Time, which began science operations in 2025, is the most promising near-term instrument for both finding Planet 9 and settling the clustering debate. Its 8.4-meter mirror, 3.2 gigapixel camera, and systematic cadence survey of the entire southern sky give it a combination of depth and coverage that no previous survey instrument has matched. Estimates suggest that if Planet 9 is within roughly 500 astronomical units, closer to its perihelion than its aphelion, Vera Rubin should be able to detect it within 3 to 5 years of survey operations. If the planet is currently near its maximum distance closer to 1,000, astronomical units detection may require a decade of operations or may not be achievable at all with the current instrument. The search is a race against an orbital clock whose position we do not know. If Planet 9 is found, the scientific consequences extend well beyond the discovery itself. A 5 to 10 Earth mass planet at hundreds of astronomical units requires an explanation for how it got there. The leading formation model holds that Planet 9 began its existence as one of the outer solar system's giant planet cores, similar in mass to Uranus or Neptune, and was ejected to its current orbit by a gravitational encounter with Jupiter or Saturn during the chaotic early phase of the solar system's dynamical evolution, before the planets settled into their current stable configuration. This mechanism is not speculative. Simulations of early planetary dynamics routinely eject multiple planet mass bodies from forming solar systems, and the architecture of other solar systems observed by exoplanet surveys shows a deficit of sub-Neptune mass planets in the intermediate orbital range, consistent with ejection operating during formation. On this model, Planet 9 is not an anomaly. It is a body that formed normally, was displaced normally, and ended up in an orbit that happens to be too remote and too elliptical for any telescope before Vera Rubin to detect. This formation model connects the Planet 9 hypothesis to one of the most persistent puzzles in exoplanet science, the super-Earth gap. Surveys of exoplanets by the Kepler Space Telescope and its successors have found that planets in the mass range of 1 to 10 Earth masses are extraordinarily common around other stars, far more common, per star, than any other category of planet. Our solar system is conspicuous in its absence of planets in this range. Earth is the most massive, rocky planet in the solar system. The next largest object in the inner solar system is Venus, at approximately 82% of Earth's mass, then Mars, at 11%. There is nothing in the 1 to 10 Earth mass range in the inner solar system. In the outer solar system, Uranus and Neptune are both larger than 10 Earth masses. The gap between 1 Earth mass and 17 Earth masses is empty in our solar system, while it is filled in almost every other planetary system we have observed. Planet 9, at 5 to 10 Earth masses, would partially fill that gap. It would suggest that the solar system did form a super-Earth-class planet, just that the planet was displaced to an extreme orbit, rather than being retained in the inner system. Our solar system would be less anomalous than the 8-planet model implies. It would look more like what planetary formation theory predicts for a system of this stellar mass. The alternative formation models are less well-developed, but not dismissible. Planet 9 could be a captured rogue planet, a free-floating planetary mass object, ejected from another star system during its formation, that happened to pass through the solar system's gravitational sphere of influence and was captured into a bound orbit. Free-floating planets are known to exist in significant numbers in the galaxy. Microlensing surveys suggest there may be as many free-floating Jupiter-mass objects as there are stars, and lower-mass free-floating objects may be even more numerous. Capture of a passing rogue planet is physically possible, but requires specific conditions. The passing object must enter the solar system's outer region during a period of sufficient stellar crowding to allow three-body capture, which is most likely in the early solar system when the Sun was still part of its natal star cluster. Whether the solar system remained in that cluster long enough, and whether a capture event of the required geometry could have occurred, are questions current models cannot definitively answer. The capture hypothesis predicts different isotopic and compositional properties for Planet 9 than the in situ formation model, and direct spectroscopic characterization of the planet's atmosphere, if it is ever found and observed, with a sufficiently powerful telescope, could in principle distinguish between them. The counter case against Planet 9, and the reason serious planetary scientists remain genuinely uncertain rather than convinced, is that the history of astronomy includes multiple examples of predicted planets that turned out not to exist. The most instructive is Vulcan, a planet proposed in 1859 by Urbain Le Verrier, the same mathematician who successfully predicted Neptune to explain anomalous precession in Mercury's orbit. Le Verrier's calculation was rigorous. His methodology was identical to the one that found Neptune. Several astronomers reported observations of Vulcan transiting the Sun. The planet was announced, named, and discussed in the scientific literature for decades. It did not exist. Mercury's orbital anomaly was explained in 1915 by Einstein's general relativity, which removed the need for any additional mass in the inner solar system. The lesson is that mathematically predicted planets, however compelling the evidence for them, must be found by observation before they can be considered confirmed. Batygin and Brown know this lesson. They have cited it explicitly. Their response is that the evidence for Planet 9 rests not on a single orbital anomaly, as Vulcan did, but on multiple independent anomalies explained by the same object. That is a meaningfully different situation. Whether it is different enough is what the Vera Rubin Observatory is going to tell us. If it is found, the implications cascade immediately. A planet of 5 to 10 Earth masses in the outer solar system would require explanation. Where did it form, and how did it get to its current orbit? The leading model holds that Planet 9 formed in the inner solar system as one of the giant planet cores and was ejected outward by a gravitational encounter with Jupiter or Saturn early in the solar system's history. A mechanism known to operate in simulations of early solar system dynamics, and known to have ejected several Neptune mass objects from other planetary systems observed by exoplanet surveys. On this model, Planet 9 is not exotic. It is a planet that formed exactly where planets form, was displaced by the same gravitational pinball that shaped the rest of the outer solar system, and ended up where nothing else went. Its existence would make the solar system look more like other planetary systems, which typically have planets in the 5 to 20 Earth mass range that our solar system conspicuously lacks, and less like the unusual architecture the 8-planet model describes. The honest state of the science is that Planet 9's existence is unconfirmed and may not be confirmed for several years. The statistical case for it is strong, multiple, independent anomalies explained by a single object on a single predicted orbit. But statistical cases in astronomy have collapsed before, when better data revised the underlying measurements. The great planet Vulcan, proposed in the 19th century to explain anomalies in Mercury's orbit, was a similar case of a mathematically predicted planet that turned out not to exist, its predicted effects being explained instead by Einstein's general theory of relativity, which removed the need for the planet entirely. Batygin and Brown are aware of this precedent. They have presented their statistical argument with explicit uncertainty quantification and have engaged directly with critics who dispute the bias corrections. Their most recent published analyses, incorporating data from additional large Kuiper Belt surveys, continue to find a clustering signal that exceeds what observational bias alone can produce. The question is whether the residual clustering is real, or whether it will dissolve as the Vera Rubin catalog grows. The Legacy Survey of Space and Time is the decisive near-term test not only for finding Planet 9 directly, but for settling the clustering argument. When Vera Rubin has cataloged 10 or 20 times as many extreme trans-Neptunian objects as are currently known, drawn from a survey with well-characterized coverage across the full sky, the distribution of their orbital orientations will either cluster or it will not. If it clusters, the case for Planet 9 becomes very strong. If it does not cluster, the primary evidence for the hypothesis weakens substantially, though the high inclination retrograde objects and the 6-degree tilt would still require explanation. The answer is expected within the first half of the 2030s. If Planet 9 is found within the next decade, a faint moving point of light appears in a Vera-Rubin image, and its motion across successive observations traces an orbit consistent with what Badigan and Brown predicted. It will be the most significant discovery in planetary science since Neptune in 1846, found the same way. By mathematics, applied to gravitational fingerprints in what we could already see, pointing to something we could not see yet. Neptune turned out to be real. The question is whether Planet 9 will. There is something worth pausing on in the idea that a planet 10 times Earth's mass could exist in the solar system we have been mapping for 4 centuries and remain invisible. We have photographed the surfaces of distant moons. We have mapped the magnetic fields of gas giants from spacecraft in their atmospheres. We have measured the composition of cometary nuclei. We have instruments sensitive enough to detect individual photons from galaxies billions of light years away. And yet a planet orbiting our own sun, sharing our solar system, shaped by the same gravitational history that formed everything else in it, may be sitting in the outer dark, unknown and unmeasured, simply because it is far enough away that its reflected light has never triggered a single detector. The solar system is not small. At 500 astronomical units, Planet 9 would sit roughly 2.5 light days from the Sun. The nearest star is 4 light-years away. There is a vast amount of space between here and there, and we have not finished searching it. The universe reserves its most disorienting revelations for the places we thought we already understood. We thought the solar system was complete. We thought the inventory was finished. We thought the major structural discoveries were behind us, archived in textbooks and celebrated in historical retrospectives. Planet 9, if it is there, says the inventory is not finished. It says that something large and significant has been orbiting our star for 4.5 billion years while we cataloged everything else. That the evidence for it is mathematical rather than photographic is not a weakness in the hypothesis. It is precisely how Neptune was found. And Neptune, when the telescope turned to the predicted position on the 23rd of September, 1846, was exactly there. The mathematics had been right all along. Whether it is right this time is a question the Vera-Rubin Observatory is currently, night by night, beginning to answer.